Well, one of the things that we definitely want to recall when we are discussing the idea of limits and trigonometric functions is the idea of continuity of a function. So let's do a little recall right here. We say a function is continuous at a point x equals c if these three conditions are met. The first one is that the limit as x approaches c of f of x exists. The second one is that the value of the function f evaluated at c is defined. Then finally, the third condition is that the limit as x approaches c of f of x actually equals the value of the function f of c. If all three of these conditions are met, then we can say the function is continuous at that point. So let's talk about a trigonometric function. Now, cosecant is the kind of function that we know has vertical asymptotes, so there will be points where the function is not continuous, and we might be interested in those kind of values. So we have a formula for finding the domain. If you recall, if I had the function, let me write this out. If I had the function, recall, uh, f of t, let's call it t. F of t was equal to the cosecant of t. What could we say? Well, cosecant of t was the kind of function that was defined as 1 over the sine of t by our reciprocal identity. Well, a reciprocal means that any point where the denominator is 0, this function is going to be undefined. So we might ask, well, where was sine of t equal to 0, so we can eliminate those points? And we said that this was the kind of function where t could not equal numbers like 0 or pi or 2 pi, right? And so on. And so what we said, instead of trying to list out all of these values like that, we said, well, just as long as t is not equal to n times pi, where n is any integer, then yeah, this is a number that will not be in the domain of our cosecant function. And so here was the trick. If you recall, we might say, well, f of x then, which is cosecant of 2x, we could find those points of discontinuity by setting 2x equal to n pi, right? Equal to n times pi. And so if we choose values of x that are equal to n, which is an integer, times pi over 2, we'll have found those kind of points. So let's check it out. Well, let's try let n equals 1, just to verify what's going on. If we let n equals 1, is the function continuous at x equals pi over 2? Well, if it were continuous at x equals pi over 2, the limit as x approached pi over 2 should exist. But if we take that limit as x approaches pi over 2 of the cosecant, s, cosecant of 2x, then we should be able to evaluate the cosecant of 2 times pi over 2, which is to say the cosecant of pi, and that value does not exist. That's not defined. It's one of those cases like when we had our trigonometric function tangent or cotangent, in which the function was undefined at its vertical asymptote. Right? That's a vertical asymptote point. And so in this case, that is the kind of point in which the function will not be continuous because it fails to meet, well, even the first condition of continuity of that limit existing. But even f of c, that would not exist right here, and so neither of the two could equal. Therefore, any value of x such that x is not equal to pi over 2 times n, or n times pi over 2, has to be excluded from our set. And so that's how we're going to define our continuity.